Good evening, and today, as you can see, we're going to get into gravity. Now, up to this point, we've known gravity as an Earth's gravitational constant, which is 9.8 meters per second squared. But today, we got to look at the universal law of gravitation. Before we really get into that, though, we've got to actually define what gravity even is. And maybe someday this will work for me without messing up. What is gravity? When it really comes down to it, gravity is simply defined as the attraction between any two objects that have mass. No matter how big or little two objects are, if they both have mass, there is a gravitational attraction between them. The other thing that will affect how strong or weak gravity is the distance between the two objects. So distance will affect them and mass will affect them. Now, one of the things is kind of obvious for you to see. The more mass an object has, the more the gravity is going to pull on it. For example, let's look. If we have a car that has a mass of multiple thousand kilograms, its attraction to the Earth is going to be higher than, say, me, who I'm about 100 kilograms. So our mass is going to affect our attraction to the Earth. Now, for us, one of the objects we have to consider the mass of is the Earth. If the Earth was bigger, the gravity would be stronger, as in our attraction to the Earth would be stronger. We'd feel like we were heavier than we really were. Now, if the Earth was smaller, we would feel lighter than we were because gravity is weaker between smaller objects. The other thing is the distance between the objects. Now, because of the numbers involved, distance to really affect for most things where we actually in the real world to measure gravity have to be enormous. I'm not talking several thousand kilometers, I'm talking several 100,000 kilometers to really have any impact at all on gravity. So even though there is a very, very, very small difference in gravity between, hey, you're at sea level and hey, you're at 1,000 feet or 1,000 meters, it's so small we don't even really care. Variances in air pressure cause a bigger difference in how fast you're going to fall. So yeah. Now, the law of universal gravitation is simply stated as F sub g, as in that's capital G as in its gravity anywhere. So it's the force of gravity anywhere is equal to the gravitational constant times the mass of one object times the mass of the other object. Doesn't matter which object you say is 1, which object you say is 2. Not really. Actually, not at all. All that matters here is the order. And then that is over the distance between the objects squared. So this is where we have to really look at things. Now, if the distance between the objects starts going up, the force of gravity between them is going to really go down. But if the mass of either object starts to go up, the gravitational attraction between them gets stronger. So those are the two real variables we got to look at here, the two ways of actually looking at universal gravity. You got mass and you got distance. If distance gets higher, your attraction or your gravity between goes down. If your mass gets higher, your force of gravity between them goes up. And of course, the G is universal gravity constant, which is universal. It's for anywhere in our universe. The only people that don't use G as 6.674 times 10 to the negative 11th Newton meter squared per kilogram squared are theoretical physicists who say, hey, in another universe, would the same stuff happen? And they kind of look at, oh, if our gravitational constant was bigger, this would happen. If it was smaller, this would happen. We're not theoretical physicists. We don't care. Our universal gravitational constant is the same. It's 6.674 times 10 to the negative 11th. If you don't remember that, it's one of the constants given to you on your reference table. I don't know if the one on your reference table is 6.67 or 6.674. You can look at that tomorrow on your own and see. So let's look at an example of this and see what it really look like. So here's our example. We have two asteroids that are 1,000 meters apart in the asteroid belt. One has a mass of 567,000 kilograms. The other has a mass of 436,000 kilograms. What is the gravitational force between the two asteroids? Now, let me grab my calculator real quick. Okay, so we're going to set this up knowing full well that we have the law of universal gravitation to use. So let me see. Can I write? Yeah. So we know F equals G m1 m2 over d squared. Now, we know this because that's our law of universal gravitation. And we know our G is always going to be, and there it is, 6.674 times 10 to the negative 11th. And then we're going to have to multiply that by our two masses. So our mass 1, doesn't matter really which one you say. And yeah, I just grabbed a calculator when I had one. Great. So our G, we're of course going to start with 6.674 to the negative 11th. Now, the best way is probably to punch it in like that, where you don't have to remember scientific notation and how to put your parentheses and all that stuff. Times 567,000 times 436,000 divided by 1,000 squared, which gives us a really itty-bitty tiny force. It is 0.000164. So that's a force that's so small, our acceleration towards each other from these two objects would be infinitesimally small. So would we really be aware of the gravity there? And this is looking at things that are huge on our scale. When we actually start having to look at universal gravity, we have to go beyond the realm of masses and sizes and distances we're used to dealing with. We have to go to masses that are mind-blowing. All right, if we look at an asteroid, these are kind of small asteroids. But these things are so big, it's kind of mind-blowing. These are small mountains floating around in space. These aren't something we would want hitting us. Now for us, our masses are so small, we would not really even have gravitational attraction between something else of our mass, even if we are less than a meter apart, because our mass just isn't there. So the two ways you can really, or the only way you're really going to have any gravity at all is you have to be enormous. You have to have mass that is way up there. And then, even if you're enormous, as you get farther and farther from your center of gravity, gravity is going to get weaker very quickly. Alright, so we're going to give you some time to practice this and actually look at this tomorrow. So that's it for today. I hope I made it under 11 minutes.